In using Coulomb's law, we're going to use this equation F equals to K Q1 Q2 divided by R squared, where Q1 and Q2, those are the values of the two separate charges, and the R is the distance separating them. So in this example scenario, we are going to be going on the atomic scale with one electron and one proton. They have the same charge magnitude, but an electron has a negative charge, one negative elementary charge, and a proton has a positive charge. So we separate these by a distance of 50 times 10 to the negative 12 meters. And in this example problem, we set Q1, one electron. It has this negative value, this negative 1.602 times 10 to the negative 19th, where one proton, this is that positive charge of a positive 1.602 times 10 to the negative 19. And we're going to take all these, we're going to multiply them together, Q1 times Q2. We're going to multiply also by this constant of 9 times 10 to the 9th Newton meters squared per Coulomb squared. And we're going to multiply these values, dividing by the square of the distance, this 50 times 10 to the negative 12 meters. And when we multiply all these together and divide by the square of the distance, we get this 9.23 times 10 to the negative 8 newtons. In the following two questions, we're now going to double the charge while keeping the constant, this distance the same, and then we're going to double the distance. And what we're trying to see is the effect on that force. So you're going to input a picture here below, following what we have here for this example on the atomic scale. When we go to the macro scale, this is now a bigger scale. In other words, we're going to go to bigger charges where we're going to be dealing with microcoulombs. So this is a negative 2 times 10 to the negative 6 coulombs. That's what this little mu here stands for. It's 2 times 10 to the negative 6 coulombs. And this mu of times 10 to the negative 6 for Q2 gives us a positive 3 times 10 to the negative 6 coulombs. We're separating them by a distance of 2 centimeters, which is 0.02 meters. And then we're multiplying by this K constant of 9 times 10 to the 9th. When we go through this Coulomb's law, KQ1, Q2 on R squared, we set up, and in this scenario, we have 135 newtons. It's really about 134.8 something newtons. And in the following two, scenario 3 and scenario 4, this is where we, once again, double the charge and see the effect on the force, and then we double the distance, and we see the effect on the force. You insert your pictures for scenario 3 and scenario 4 here. After you get through all that, after you do all that, you can click on this, use this site to check your work, and you can set up that same scenario. If I go to the atomic scale, I can go to this atomic scale, and I can separate these by a distance of 50 picometers by setting my Q1, Q2, and I can go to this negative 1 and a positive 1, and we get the same value of this 9.23 times 10 to the negative 8. We can go to the micro, from the atomic scale to the macro scale, where we can change those values, negative 3 and positive 2, separating them by a distance of 2 centimeters, and we get this 134.8 newtons, which is about 135. So check your work on this using that site, as well as doing the work by hand.